Alright students, this is Mr. Weirman and welcome to the Friction Lab. You're not going to see my face too much because of the fact that I can't switch views during the course of the video. I'm making this video with my phone. So this video is for those that have missed the Friction Lab that are absent. If you are a hybrid student or if you're distance learning, this is how you're doing the lab. Alright, so I think probably the easiest way to do this lab is to have this video open on one tab and then have this Friction Lab, this Google Doc Friction Lab open on the other tab, because I'm going to be going back and forth between those two. That way you can pause the video from time to time and then record the data in the Friction Lab. So I have two tabs open, one of the Friction Lab, one of this video. Alright, so what's the stuff we're going to need? Pencil just to write stuff down. We need a metric ruler. We're going to use these three blocks of wood. We're going to use these three blocks of wood. We're going to use some colored pencils as some dowels, actually. And then we're going to use just my coffee table. So this is just the coffee table in my house. And this is just a rubber mat from school. And we're also going to use this thing. This is called a spring scale. Many of you that are anglers may be familiar with this. So this is a spring scale. This is what we're going to use to measure our force. As you can see, if I kind of hold this up, it states 10N. So this spring scale can measure up to 10 newtons, and you can see it's graduated from 1, 2, 3, 4, 5, all the way up to 10. And then there's 5 lines between each whole number. So each line, each smaller line is worth 2. So now what's a newton? Well, a newton is a measurement of force. The definition of newton is the amount of force that it takes to move 1 kilogram of mass, or accelerate 1 kilogram of mass at a rate of 1 meter per second squared. So that's our metric definition of a newton. Alright, so let's get to our purpose. What is the purpose of our lab? Alright, so the purpose of the lab. What are some factors that affect friction? Ultimately, what we're studying here is friction. Learning target 2, C. Understand and describe how friction affects motion. Be able to give examples for and identify types of friction. Static, kinetic, rolling, sliding, and fluid friction. Describe situations of how friction can be both helpful and harmful. So remember, friction is just the force that resists movement. The force that resists movement. All right, so we've already gone over our required supplies. So really, we're going to do 2 things in this lab, or 3 things, right? Part 1 is we're going to compare. We're going to compare the amount of friction, or the amount of force that it takes to overcome different surface areas. So we're going to do a pull test on this side. So how much force needs to be to overcome this amount of surface area. And then the other one is how much force needs to overcome this amount of surface area. All right, so that's part 1 of the lab. Let's see, part 2 of the lab is investigating mass. What is the relationship between mass and friction? So we'll initially pull 1 block, and then we will pull 2 blocks, and then we will pull 3 blocks. So that's the second part of the investigation, is what's the effect of mass on friction. All right, and then the third part is texture. Which is how will these blocks move over, say, this coffee table versus over this rubber mat. So we have different surfaces of smoothness. How will friction be reduced, increased, or not affected at all? And then the last one, part 4, sliding friction versus rolling friction. That's where our colored pencils come into play. What would happen if we use these colored pencils and we move the blocks over colored pencils, and we compare rolling friction compared to just sliding across the table, sliding friction. All right, so that's just an introduction to the lab. Like I said, you want to make sure that you have this lab out, have this lab open on one page, and then watch the video on the other. All right, so what's the first component? The first component is investigating surface area, and it states, calculate the surface area of the largest face of the wooden block with metric measurements using a ruler. Centimeters would likely be most appropriate. Do the same for the next smallest surface area of the block. Show your work for each calculation below. Okay, so now we've done our 3-step calculation here many times. Remember, the 3-step process is 1 is the formula, 2 is the numbers, 3 is the actual calculation. Well, we're calculating the area of this, so the area is just simply the length times the width. So there's our step 1, right? Our step 1 is just to simply write down area equals length times width, right? Length times width. Well, that's where our metric ruler comes into play. And let's measure. All right, so I'm going to line this up on the 0 and come on in. And let's call this 13.3 millimeters. 13.3 millimeters. So our length, our width, area equals, pardon me here, area equals, so we have 13.3 centimeters times, let's measure, trying to keep the camera as steady as possible so you don't get nauseated. Let's call this, looks like this, let's call this 20 point, what do you think, students? 20.4, let's call it 20.4. All right, so we have length times width, or in this case, width times length, so 20.4 centimeters. All right, so that's our data. You can go ahead and plug that into your Google Doc, and then I'm going to have you do the calculation. So that's the large area. And of course, we also have to repeat the process with this area, this surface area as well. All right, so, well, we've already established the length, right? We've already established that the length is, what do we say, 20.4? So that's not going to be different. This is going to be 20.4 again. Only now our width is going to be 10, 20, 35, 36, 37. Let's call it 3.8, 3.7 centimeters. All right, so again, our formula is area equals length times width. Area is length times width. What is our numbers? Our area equals, right, so we already established it's 20.4 centimeters, right, times, right, 3.7 centimeters. Really, those are the numbers we came up with. All right, so again, I leave it to you to do the calculation, and that's going to be your surface area, right? But now, before we go back and actually do the lab, let's jump up here and consider the stating your hypothesis. I want you to answer these 3 questions. How will decreasing the surface area of a block affect the friction measured? Will it, right, will the friction increase, will the friction decrease, not be affected, or will it decrease? So you have to pick one of those 3. How will increasing the mass affect the friction measured? Again, do you think it's going to be increased, not affected, or decreased? Select one of those 3. And then what about surface texture, right? Will changing the surface texture, going from smooth to rough or rough to smooth, increase the friction, decrease the friction, not affect it, or decrease it? All right, so just take a minute, pause the video, make those 3 predictions, and then we'll move on. All right, so how do we actually do the lab? Well, let's set the block up. We're going to start with the block on the table. And we're going to use our spring scale. I'm going to hook our spring scale up here, like so. We're going to turn it so that we can read it. Now remember, we have static friction and we have sliding friction. And static friction is greater than sliding friction. So when I pull this, you're going to see the number is going to be greater, and then the block will start. So this is our static friction, and then as the block starts to move, it gets less, and you can see now that we're moving how many newtons. All right, so just to back up, let's do that again. Let's do our measurement of here is our static friction. I'm going to come into that, give it a chance to focus. looks like 2 newtons for static friction, and then 0.8 newtons for sliding. So let's go ahead and put that in our data table, right? Static friction was 2 newtons, and our static sliding friction was 0.8 newtons. We're going to repeat that process 2 more times, and then that way we'll take an average. Alright, so same thing. Zoom in on our scale. Ooh, that looked like more like 2.1. Let's back up. Let's try that again. Okay. Ooh. That was a lot less, wasn't it? So there's our 2. Oh, that's looked like 2.1. And then that's a lot closer to 1. Alright, so we're going to call this 2.1. And we're going to call this 1 newton. Let's do one more trial. So again, we're sliding the block across, you can see. Ooh, that looked, let's turn it so we can see the number. Oh, I think that was 2. And again, yeah, that looks more like 9. Alright, so again, 2.0 newtons are static friction, and then 0.9 newtons are sliding friction. Alright, so, I put that in the wrong spot, didn't I? That data is supposed to go up here. Alright, so, I was rushing myself, students. I want you to move this information up here, right? Because that was supposed to be 2 blocks, and I put that in the wrong spot. So let's just do this: 2.0, 2.1, and 2.0, and then over here we have 0.8, 1.0, and 0.9. There we go. Alright, so I'm going to erase this data because that's the 2 block data. That's ahead of myself. I just write that out of the way, and same thing here. Let's get this out of the way. I know this isn't the same as actually doing the lab, but it is better than nothing. Okay, alright, so now that was our large surface area, right? Now we have to do the same thing with our small surface area. 3 trials with a small surface area. So that means pulling the block this way. Now remember, we made a prediction, right? What was your prediction? Did you think that less surface area is going to have more newtons, less newtons of friction, or the same of force? Alright, so again, let's zoom in. Now we're on the lot less surface area. Turn this so it's in the light, and ooh, looked a little less, didn't it? That looked more like 1.6, and then, oh, the light's kind of everywhere. I'm going to move the block so we're out of the light a little bit. Let's try this one more time. Alright, so here is our block. Our static friction is 1.2, and our sliding friction looks like 0.9. Okay, so again, in the data table on the small surface area, right, the static friction was 1.2 newtons, and this was 0.9 newtons. And as always, let's do 3 trials. Let's back it up. Here's my spring scale. That looks like, ooh. Oh, that was 2, wasn't it? Alright, that second one was definitely, I wonder if my first reading was a little soft. So 2.0 newtons, and then again this looks like 0.9 newtons. I'm going to back this up one more time. Be super precise here and try and be careful. Alright. Ooh, it looks a lot less, doesn't it? Yeah, 1.1 again, and then 0.9. It would appear that it takes less static friction, but the amount of sliding friction is basically the same. All right, so again, calculate your averages there. All right, so we did our 3 trials of the large surface area, our 3 trials of the small surface area. Now, let's try 2 blocks, right? 2 blocks, and we're going to use the same thing, stacked on top of each other. Again, do the 3 trials, right? Then to record the average. And we're going to stick with the large surface area. So here's 1 block. Now, let's put on 2. So now we have 2 blocks. All right. 2 blocks. Ooh, that looked like 4.1 and 2. All right, so again, get this cleaned up nice. So our first trial, we had 4.1 newtons and 2.0 newtons of force for static and sliding. Now remember, we're going to do 3 trials. So here is trial number 2. Let's get it so we can see the numbers. Oh, look at that. 5 and 2. Wow. So that took us 5 newtons. That's a 5, students. 5 newtons and another 2. So 5 of the static friction and 2 of the sliding. Again, remember, static friction is greater than sliding friction, which means that once it's moving, it takes less force. All right, so one more time. 2 blocks. Oh, that looked, oh, let's try that again. I wasn't in frame, was I? All right, that looked like 3.9. And then 2 again. All right, so our static friction is kind of all over the place. That may have to do a lot with the table. Let's call it 3.9. And then this was definitely a 2. All right, so again, I leave it up to you to calculate those averages. All right, so now let's add a block. Let's take a 3rd block. Predictions, students? I think we're pretty confident it's going to go up. Now, is it going to go up proportionally? Guesses on what the number would be. All right, let's see here. Get the camera way out here. 5, 6, 7. Ooh, that looked like 7.5 and 3. All right, so again, so now this data table, 3 blocks, 7.5 newtons, and 3 newtons of sliding friction. Let's go again. Get in here close. Oh, that was over 8. That was 8.1. And 3 again. Again. 8.1 newtons of sliding friction and 3 of the static. Oh, sorry, 8.1 of the static and 3 of the sliding. One more. Ooh, that looked a lot less. Let's try that again. Oh, that looks like 6. Right, I'm not happy with that number. Let's go back to where we started. I gotta pay attention here. That was definitely 6. 6 and 3. Okay, so again, our numbers are kind of all over the place for our static friction, 6.0 newtons and 3.0 newtons for static. All right, so now we have tested, well, we've done 2 parts, right? We've tested the 1 block, the 2 blocks, the 3 blocks. We've also tested the broad surface area versus the small surface area. All right, so let's move on to texture, right? So now what does texture tell us? Repeat the process described in part 1 above with one block, large side facing down, but now drag it on the rubber mat instead of the smooth table. And we'll record the data here. So here is our surface data table. So we're going to do 3 trials. Now we're going to do 3 trials with one block on this rubber mat. So now it's a different surface, right? It's a different surface compared to the smooth table. All right, so let's go back to that. Here's our first trial. Static friction is, ooh, that looked like 2 and 1.1. Well, maybe this table one, right? 2 and 1.1. All right, let's do another one. Back it up. Trial number 2. Oh, that was like 1.9 and 1.1 again. All right, so 1.9 and 1.1 newtons of force. Trial number 3. We're almost done here, students, and you can calculate the data. Let's zoom way in. 2 again, and that looks like 1.2. All right, so again, 2 newtons of force, and then 1.2. Again, you can calculate the average. All right, so again, that's comparing the rubber mat to my coffee table. Maybe I should have done the rubber mat and my kitchen table on my countertop. All right, so now the last one is the rolling friction, right? So remember, before we do that one, we got to fill in our hypothesis. Let's look at part 4, sliding versus rolling. What do you think will happen to the force of friction required to pull the block if you placed it on rollers? Do you think the friction is going to increase? Do you think the friction is not going to be affected? Or do you think the friction is going to decrease? All right, so let's take our rollers. Our rollers in this case are these colored pencils. Simple enough, right? Got the lab over here. Here's our colored pencils. Or sorry, here's our rollers. Now I'm going to take our block and I'm going to put it on the rollers. So now the block is on the rollers. And now let's do our 3 trials. This is data table 4. Oh boy. I think we can see already we're going to have to be super precise with our measurements here. Put our pencil down, get that in there, adjust this so we can see the, alright. Oh, I'm going to calibrate my, just a second, students. I think my calibration is off a little bit. Oh, looks good. Sorry about that. Just making sure that the balance was zeroed out. Alright, the spring scale. Okay. This is not going to be much. This is actually kind of tricky. Let's turn this so we can see it. Stay with me, we're just about done. Oh boy, that looks like almost nothing. Let's back that up. I might need more colored pencils. My first trial looked like it was 0.2 newtons, right? 0.2 newtons. Which was very little. Sideways. Hold on 1 second, students. I've got to loosen this up a little bit. Or tighten it up a little bit, rather. Alright, let's try this again. 3 times a charm. I was putting it sideways. The scale was off. Alright, so here we go. Again, look like a 0.1 Newton. So almost no friction here to overcome. You can almost use more colored pencils. One more trial. Same thing, 0.1 newtons. 0.1 newtons. Now with respect to our static friction, right, and our block of wood, we can go back to our original data, which we took off of. We can go back to the data off of one block, off of the large surface area. So we can just take this data. We've already done these trials, right? Surface area of the block. So 2, 2.1, and 2. All right, so 2, 2.1, and 2. Oh, you know what? I tell a lie. That's my mistake. We don't want those numbers. We want these numbers right here because they were basically the same. 0.2, 0.1, and 0.1. All right, so there was almost no difference between our static friction and our rolling friction. At least our spring scale was not precise enough. All right, so in conclusion, wrapping this up, right, so you can get on with your analysis. You should have made your predictions already. Calculate the surface area of the large and small side. There's the data for the large surface area block. There's the data for the small surface area block. There's the data for 2 blocks, large surface area. There's the data for 3 blocks, large surface area. There's the data for the rubber mat versus the coffee table. And there's the data versus the, block on the dowels, the rollers. All right, that's it. Do the calculations, calculate the averages, and then go ahead and make sure you do the analysis questions. Analysis questions are right here. Thanks, students. Bye.